prominent issue today is the COVID-19 pandemic. Many indoor locations have implemented mask mandates in order to control this. But with these new mandates, there has been conflict, whether it's people not adhering to the standard entirely or the improper wear of masks. In order to solve this problem, there needs to be a solution to ensure these mandates are followed cheaply and effectively. With this problem in hand, it brings us to the concept of the Rona. The Rona is an affordable autonomous vehicle that is capable of surveying high COVID-19 infection rate areas with live mask mandates to ensure that the mandate is being followed. The Rona is capable of detecting faces to tell if a mask is worn or not, and is able to actively avoid foreign objects in range of a sensor, as well as output a visual cue for when an individual is caught not wearing a mask.
In this section, we will be discussing the software and hardware requirements for basic driving functionality. For hardware, this project uses a Raspberry Pi connected to a four-wheel drive capable motor driver board that came included with the Yaboom remote-controlled car kit. This board connects to DC motors that are rear-mounted on the car's body. Internally, this motor driver board uses CMOS transistors to supply the required power to the motors. These DC motors are operated at 12 volts and require half of an amp to run at normal operating frequency. These motors are connected to the front, non-driven wheels via caterpillar track, mechanically linking the front and rear wheels. As a high-level overview of the driving function used in the system, the Pi can execute one of 5 commands at a given time. These commands are for driving in the 4 cardinal directions at a given speed, and a stop command. The speed is determined by the duty cycle of a PWM signal that is sent to the motor driver board from the Raspberry Pi. For a tight turning radius, the car implements a zero-turn system. This system entails driving the motor of the turning side forward while driving the inverse in reverse.
So for our autonomous driving portion of our car, we use a Intel RealSense L515 LiDAR, which was provided by our professor. So the code which was actually written for this was actually in Python. So whenever we would start up our car, the code would automatically run as well. So the depth values were actually able to grab from the Intel RealSense application by using a script in Python. So the script in Python will open up the Intel RealSense application and grab the certain pixels out and give us the depth values for each one. So by doing this, you have a large amount of computational power you need to do so. So to try to alleviate this issue, we use a checkerboard pattern. This checkerboard pattern lets skip pixels, so it would go 10 on the x-axis and 10 on the y-axis. Also, if a pixel is seen as too close to the car, it would actually skip down another 10 pixels on the y-axis to try and see if it actually was noise or not as well. So on this slide, you can see an image actually from the LiDAR. So each one's actually color-coded with how far away the object is from the camera. So you see your reds are your farther distance away, and then the blues are the closest part away. So for our camera, we actually had to bring the camera up a decent amount to where the base of that chair is to try and cut out all the noise from the floor. If we didn't, the car would just randomly stop and wouldn't move at all. So here's a block diagram for autonomous driving. So at the very beginning of the program, the Intel RealSense LiDAR will start up. The LiDAR will then start performing the checkerboard algorithm. So if a object was seen within 0.7 meters, the object will perform a backup. If the object is seen on the left side of the image, the car will turn right, and if the image is seen on the right side, it will turn left. If it's seen in the very center of the image, it would perform a Y turn to the left. If the car is ever seen, there's nothing in front of it at all, within that 0.7 meter threshold, it will keep on driving forward. There is one hiccup with the LiDAR is that anything underneath the point 0.5, like point 0.5 meters, the LiDAR will not pick up at all. So we try to counteract this by using the 0.7 meter threshold.
For our facial recognition and mask detection segment, we wanted to use image processing for the mask detection, and therefore we trained a neural network which utilized OpenCV and Keras along with TensorFlow to train the dataset. This dataset consisted of approximately 4,095 images, which included faces with masks and without masks. We attained an accuracy of 92% after training the dataset for about 10 epochs. And the way the algorithm would function is that if it detected the pixels of the face within the bounding box, the box would be displayed in green. Otherwise, the box would be displayed in red. And this bounding box framework was determined using the mask detection algorithm as referred to here. And when it was deployed on the Pi, instead of the bounding box being displayed, we would have the LED lights turn green or red, as the case may be. Here, as you can see in our algorithm, when the Pi was started, it would basically control the input from the user, and as it would move along, the scan would be initiated, and once it finds pixel representing a human face within its bounding box, it would check for if those pixels had a mask around the mouth and the nose, and if it was there, it would continue to carry on its task. Otherwise, it would display in red, and another scan would be initiated to check if there's a mask or not. During the training phase, we realized that the performance of the model that we had trained was very slow due to the computations it was processing. Therefore, we decided to skip every 5 pixels, which would reduce the computations and improve the performance of the model. When we also incorporated a secondary Raspberry Pi, it further helped to detect the mask infractions faster, and about 2 seconds was saved for every time we had reduced the 5 pixels. After tuning our final model, we further added few function calls just to ensure foolproof testing of the model. Therefore, we clicked different snapshots using the Pi's camera and ran them on the model to see how the mask predictions were depicted. And as you can see, when there was no mask worn, the bounding box was shown in red, and when a mask was worn, the bounding box was shown in green as expected.
Try to turn the volume off.
So it's a off, and he's going to get the first down. Whitfield forces him out, but it's past the 6. When you watch the team this week, and we're looking for ways that Washington could sustain success, you thought that Heineke would need to do it.
Try to turn the
The overall performance of the Rona Cop has been exceptional, with the maneuverability far exceeding the initial expectations set during the initial design process, as well as the LiDAR sensor object detection, far exceeding the initial expectations by 4 meters when it came to detecting and processing objects. For the mask detection, while mounted on the RC body, during the initial expectations of 80% accuracy. When stationary, we were able to measure 90% effectiveness, but when in motion, this dropped to 60%.